everyone. Welcome back to another Physics in the Flesh video, number 69. Video 68 was static friction on an incline, part 1. This is part 2, but with kinetic friction. Okay. The coefficient of kinetic friction for a 25 kilogram bobsled on a track is 0.10. What force is required to push it down a 5.5 degree incline and achieve a speed of 58 kilometers per hour at the end of 57 meters? So, again, the difference between this and video 68 is that in this case, the product is not only moving, but it's accelerating. But my first step is always going to be the same. I'm going to draw a Freebody diagram, and I'm going to keep it really simple. So my incline is going to be this triangle, this ramp, and my bobsled is going to look like a box, right? Because you want to keep it simple. Now, next thing you want to do is draw your forces acting on the box. Obviously, because the bobsled has mass, it has a force of gravity, which is angled straight down towards the center of the earth. So that goes straight down. Okay? Because it's on a surface, there's a normal force, and the normal force goes perpendicular to the surface, away from the force of gravity. Okay? We know that this bobsled is getting pushed down the incline. Okay? So there's going to be a force parallel but down the incline. We can call that FP for force push. And of course, there's a frictional force opposing that. And because the bobsled will be in motion, that frictional force is kinetic. Now, just like we saw in video 68, because you see how these three forces are all perpendicular to each other, but then FG, which is the usual y direction, is at a weird angle relative to the other ones. Because of that, we want to establish a new coordinate system. And in this case, it's going to be where x, positive x, is down the incline, and positive y is perpendicular to the incline. That way, these three are already in the xy coordinate system, and the only one we have to change is FG. So in order to do that, I'm going to drop down a line towards the vertical, and therefore FG makes an angle theta with the vertical. Now again, if you remember watching video 68, this angle right here turns out to be the same angle that the ramp is inclined at relative to the horizontal. And we're told in the question that that's 5.5 degrees. Okay, so we know that's 5.5 degrees. Therefore, this theta is also 5.5 degrees. So one last adjustment to make in the question and in the free body diagram. Since I'm already here, I'm going to draw it. Because this is FG and we've drawn it relative to the vertical, we can actually break up FG into components, x and y components. That was the whole point of doing this in the first place. So if I draw another line to this vertical, that line is going to be my FGX. Okay, and then that vertical line is going to be FGY. So now I've got FGY going down, I've got FGX going to the right, I've got FFK going to the left, FN going up, FP going down to the right. All right, so there we go. Now, I've got the free body diagram, and as is procedure with these types of questions where you have an incline, you've got many forces. I mean, this is a Newton's second law problem. F net equals ma. And it seems like we're given the mass, which is good. We're looking for one of the forces. We can figure out some of the other forces because we have the mass and the coefficient of friction. Okay? But we're missing one of the forces. So the third piece of the puzzle in Newton's second law is acceleration, which they also don't give us. However, they give us an ability to find it by telling us the speed at the bottom of a 57-meter long incline. We know it's being pushed down the incline. In other words, it starts off with a speed of 0, and we're looking for acceleration. Acceleration, after all, although you use it in Newton's second law, it is a kinematics quantity. Okay, so I need to find acceleration, but now hold on. To find acceleration, I need to use the speed, right? But the speed is quoted to us in kilometers per hour. And we know that for physics problems, you should quote speed in meters per second. Okay, so that's going to be my very, very first step. Okay, so V is equal to 58 kilometers per hour. Now, in my earlier videos, I showed you how to convert units. So I'm going to do it again here. It's very straightforward. All you need to do is multiply by 1 every single time you need a unit to change. For example, I need the kilometers to change to meters. I multiply by 1. I need the hours to change to seconds. I multiply by 1 again. Okay, why am I multiplying by 1? Well, if I multiply by any other number, I'm going to change the question. So my ones are going to be my unit conversions. So here we go. 58 kilometers per hour. So you replace the ones with empty fractions. Okay, so I'm trying to get rid of the kilometers, so I'm going to put that down here, right? Because they have to cancel. And I'm trying to get meters out of it, so I'm going to put meters on top. Okay, then you ask yourself, what ratio of meters to kilometers equals 1? Okay, so 1,000 meters is equal to 1 kilometer. So this is equal to 1 here. Okay, next, I'm trying to get rid of hours, so I'm going to put hours on top, and I'm trying to get seconds out, so I'll put seconds on the bottom. Again, ask yourself, how many seconds is in 1 hour, or what ratio of seconds to hours equals 1? Okay, so 1 hour contains 3,600 seconds. 60 seconds in a minute, 60 minutes in an hour, 60 times 60 is 3,600. Okay, so by doing this, see, your kilometers cancel, your hours cancel, and you're left with meters per second. So pretty much what this calculation comes down to is 58 times 1,000 over 3,600 meters per second. Okay. 1,000 divided by 3,600. Okay, so essentially what you're doing here is you're dividing it by 3.6. Okay, so when you do that, you're going to get out 16.1 meters per second. So there's your speed. Okay. And that is technically your V2, or your final speed, because you're making it to the end of the ramp with that speed. My initial speed, V0, is going to be 0, right? Because it's being pushed. So we've got V, 16.1, V0, 0, and we're also given the distance down the incline. And because that's in the positive x direction, I'll call that delta x. Delta x is equal to 57 meters. So next step is to plug these into a kinematics formula. So here I go. So the kinematics formula that relates all three of these quantities and allows us to find acceleration is 2a delta x equals v final squared minus v initial squared. Now again, we're looking for acceleration. Now we know something in this equation 0, and that's v naught. That is 0, so that makes it a bit easier. That goes right away out. And for the rest of the problem, to get a by itself, divide both sides by 2 delta x. 2 delta x. So that cancels out the 2 and the delta x on the left. You're left with acceleration equals v squared over 2 delta x. Okay, so at this point we just need to plug in our numbers. A is equal to v squared, we just found out to be 16.1. 16.1 meters per second squared over 2 times 57 meters. And when you punch that into your calculator, you're going to get acceleration is equal to 2.27 meters per second squared. Now, just to make this a little bit more precise, because it's acceleration down the incline in the x direction, I'm going to call this AX. Okay, so hopefully that's okay. Okay, so now we've got another piece of the puzzle. We've got AX, we've got the mass. Okay, so we can use F net equals ma to find the missing force. Okay, so that's going to be our next part. Okay, F net equals ma is going to make heavy use of the free body diagram. Okay, so we're dealing with net force in the y direction, the x direction, because in the y direction, the bobsled is not accelerating up or down, so the net force is 0. In the x direction, however, we get F net x equals max. Okay, so if you take a look, in the x direction, we actually have 3 different forces. We've got Fp in the positive x direction, we've got Fgx in the positive x direction, and Ffk in the negative x direction. Okay, if you're wondering why Fgx is in the positive x, it's because based on the center of the object, this part of the vector is more towards the right. Okay, so if this is the center, it's more to the right than it is to the left. And we defined right to be our positive direction. So we can replace F net x with Fp plus Fgx minus Ffk equals max. Okay, and what we're looking for in this problem is Fp. That's what we're trying to solve for. So I'm going to get everything else going to the right side of that formula. Okay, so I get Fp equals MAX. And you bring the FFK over, it becomes positive. You bring the FGX over, it becomes negative. So plus FFK minus FGX. Okay, the next step is to rewrite these in more simplified forms. Okay, we know that the force of friction is given by the product between the coefficient of friction and the normal force. So it's going to be plus mu k Fn. Now FGX, okay, so this is a component of the actual force of gravity. So let's just quickly go back to the free body diagram, right? So we've got our different forces. Take a look at FGX and FGY. They make right angles with each other. Okay, and the actual FG is the hypotenuse of this right angle triangle. Now what I'm going to do is I'm going to redraw that triangle down here. So let me just do that so you guys can see. Okay, so if we've got FG going like that, we've got FGY, and then you've got FGX. These two meet at a right angle, right? We know that this angle right here is 5.5 degrees. So take a look. I mean, this really comes down to SOHCAHTOA. FGX is equal to the hypotenuse times the sine of this angle. Okay, so the hypotenuse is FG. The sine of the angle, sine 5.5 degrees. Okay, so an FG is just mg. mg sine 5.5 degrees. Okay, that's FGX. Similarly, FGY, okay, it's adjacent to this angle, so we're going to say it's equal to mg cosine 5.5 degrees. Okay, so that's just a bit of work on the side there. Okay, so let's get back into this problem. So we're at MAX plus mu KFN. So minus FGX means minus mg sine 5.5 degrees. Okay, so we plug that in. Now, mu k Fn, the Fn, well, what is the normal force here? Right, so there's no equation for normal force. You have to determine it based on Newton's third law. Okay, what force is it opposing? So here we go back to the free body diagram. Okay, so we've got normal force here. We know that the bobsled is not accelerating up or down, and the only other force in the y direction is FGY. There's only those two. Okay, and because one's going up, one's going down, therefore they must be equal in magnitude to each other. Therefore, FGY has the same magnitude as Fn. Okay, and that's what we're going to plug in here. Fn is just going to be FGY. And we know what FGY is. We just simplified it. It's mg cosine 5.5 degrees. Okay, so I know there's a lot of substitutions here, but just bear with it. MAX plus mu k, again, mg cosine 5.5. In fact, guys, you don't really have to plug in the 5.5 yet. You can just leave it as theta. And technically, that would be more proper. But since I've already gone ahead and done it as 5.5, let's leave it like that for now. It's okay. Okay, so we got those angles. Now, another similarity I see, I have mass appearing in every single term. So I'm going to factor that out. Okay, so if I factor it out, from the first term, you're left with AX. From the second term, you're left with mu k g cos 5.5 degrees. From the last term, you're left with g sine 5.5 degrees. Okay, now I can't really simplify the equation any further, so I'm going to start plugging in my numbers. Okay, my mass of the bobsled is 21 kilograms. Okay, the acceleration I determined for this question was 2.27 meters per second squared. Okay, and then plus mu k, it was given to us in the problem as 0.10. G is 9.8. Okay, cosine of 5.5 degrees. And then minus g, which is 9.8, sine 5.5 degrees. So there you go. Okay, so this entire expression in the middle, there's a lot of stuff happening here, and to prevent you from making a mistake, I would say solve each part individually. So enter that in your calculator, and then draw the next line for that. So 21 kilograms, 2.27 meters per second squared. Okay, this quantity here is 0.9755, and that last term there is 0.9393. So now we can enter this all in our calculator, and we're going to get 21 kilograms times 2.3062. And the unit for this, because these are all technically coming out to be accelerations, the unit comes out to be newtons per kilogram. Okay, and that allows us to cancel out the kilograms. Okay, so we're almost done here. When you enter this into your calculator, you're going to get 48.4302, which by rounding it, we get the F push to be about 48 newtons. Now, because this is a vector quantity, you have to indicate the direction with it. And F pushes 48 newtons down the incline. Okay, and that's it. So just to recap what we had to do in this problem, we're using Newton's second law. So it has three different objects in there: net force, mass, acceleration. We're given mass. We're looking for one of the forces in the net force combination. So we had to find acceleration. And we did that using kinematics. Okay, final speed, initial speed, displacement. Find the acceleration, okay? Use the Newton's second law in the x direction, plug in your net forces in the x direction, and just work it through and be able to pay close attention to the components, FGY and FGX for FG. And overall, guys, that's it. I hope you enjoyed the video. If you did, be sure to click that like button and subscribe to Physics in the Flesh so you never miss a video from me. Thank you guys so much for watching, and I will catch you in the next video.